Good day, I'm Zhanali Imambekov, and this is my 2024 Computer Systems Research Project for Period 1 Yilmaz, Forest Fire Risk Assessment and Target Detection Model for North America. So the world is facing a severe problem, forest fires. Every year we're losing millions of acres of forest vegetation and grassland due to forest fires. And because of the way forest fires work, the more fire activity there is, the more CO2 is released by burning vegetation. The more CO2 there is in the atmosphere, the more the temperature of the globe increases, which increases the chance of fire activity happening again, which creates a positive feedback loop that simply will keep escalating with more wildfires and higher temperatures. Even now you can see in this graph below that although the number of fires has been going down, the average amount of acres burned per year has been only going up. And this feedback loop will keep moving forward unless we do something now. Thankfully, a number of solutions have been proposed. Microsoft has its ZeroRI, which is a machine learning training tool that can use topographical data to detect and predict wildfires. There's a company in California called PanOAI, which has been setting up watchtowers with very high ultra-fine cameras that can detect wildfires as they occur in a 15-mile radius. A startup in Germany called Aurora Tech has been revolutionizing nanosatellite swarms that in the atmosphere can detect wildfires with high precision. A novel solution was proposed in China just recently called paper chip technology, where they use various types of ions to detect temperature changes and create electricity, which can then be used to power transmitters, which can then be used to send signals, which effectively correlate into instantaneous detection of wildfires as they occur. This doesn't mean that the chips themselves have to be on the burning material, but research has shown that they're relatively cheap, costing only about 4 cents per chip, and they'll be environmentally and economically friendly. And all these professional methods generally boast 90 to 95% accuracy in all cases. However, all these methods are either serious academic work or commercial endeavors. They are by nature disparate and not exactly connected. Although wildfires are a global problem, people aren't approaching them together. And there's also a serious lack of resources that novices or people who want to get into the field of researching forest fire solutions don't have the necessary data or skills to use them, because the majority of the data is held in formats that only professional data analysts can use. So, my project aims to compile 3 different models for forest fire detection, risk assessment, and spread modeling, and then compile the datasets I use into a single repository that the future researchers can use as a baseline to create their own models. This dataset will be completely free. It will have a complexity and depth that other solutions don't have, as they focus specifically on only one aspect of combining wildfires, and generally it will hopefully incentivize more teamwork towards solving the global issue of forest fires in the future. But just before we move into technical details, let's cover some background. This project extensively uses AI, which is standing for Artificial Intelligence, the computer science field related to training computers to mimic human capabilities and perform specific tasks. Within AI, there's a field called deep learning, which is a family of machine learning methods based on simulating neural networks with representative learning. Neural networks are a sort of subset of machine learning that simulates a relationship through a series of nodes. In this project, we'll be specifically using primarily convolutional neural networks, which are useful primarily in classification computer vision problems. Essentially, convolutional neural networks apply what's called a kernel towards an image to get a dot product of that value. And through repeated use of kernels, they can abstract features to detect angles, shapes, and eventually classify images on their own. So, method. Our goal is, again, to create deep learning algorithms to train a neural network to identify forest fires from images, predict wildfire expansion rates and expected coverage, predict the risk of wildfires actually occurring, and put all these datasets together in an easily accessible format. So initially when I was doing this project, I found, specifically for goal 1, detecting wildfires imagery, I found a Kaggle dataset called Wildfire Detection Image Data. It was roughly 19,000 images of various pixel sizes. Roughly 97% of data was for training and roughly 4% was for testing. And I trained a model using 3 layers of kernels and convolutions, using back normalization and max pooling to efficientize the process. And in general, the network was supposed to spit out 2 classifications, a wildfire and a wildfire classification. Unfortunately, after over 175 epochs, the network didn't achieve the network did achieve a very high accuracy, roughly 0.96% accuracy. However, I encountered a problem. This dataset primarily composes of wildfire images from the human level, from ground level. The majority of datasets compiled for wildfire detection won't come from ground level. They'll be from satellite imagery or unmanned aerial vehicles. And so, scrapping this idea, I moved on to another dataset called Flame 2. This is a dataset compiled by a bunch of researchers in 2022, and the primary thing I want to focus on was the 53,255 pixel set of IR images they compiled from using UAVs, unmanned aerial vehicles, to take pictures of wildfires as they're occurring. As a repeated experimentation, I decided to use just a simple dense neural network to train this method, where I would take in these images, which were pretty small, 255 pixels square size, and I'll feed them for roughly 4 layers of dense neural network to spit out 2 values. These images were, by the way, classified by 2 metrics: if they were on fire or if they had smoke in the image. This is useful because IR images not only detect, because when classifying images, we have to distinguish between images that have smoke and don't have fire. Because images that only have smoke but fire can be read as false positives for such cases as factories, volcanoes, and so on. While images of only fire but no smoke might be false negatives for, let's say, campfires or other sources of extreme heat. And eventually, after roughly 150 epochs exactly, we reached 99.6% accuracy, very high. An example of the classification here would be this image on the right, where we show the normal RGB value of the image and the IR image, and here the image spits out that yes, there is fire and yes, there is smoke. So that's goal 1 accomplished. Moving on to goal 2, I experimented with a dataset called Next Day Wildfire Spread, which is roughly 3.96 gigabytes of 13 fire masks. These masks compose of elevation, wind direction, wind speed, min temp, max speed, so on. Basically topographical data values that we can use to predict the spread of wildfires. Unfortunately, the method I used, which was roughly a convolutional neural network that accepted these 12 initial masks through 7 layers of kernels, did not reach a very high accuracy, only 33%. And it took a very, very long time to reach that percent. Roughly 80 epochs that each took 2 hours each. It was simply too inefficient, so I scrapped that idea. And I moved on to another dataset. This dataset is called Wildfire DB. It's a dataset of roughly 17 million data points of 394 different values. But the one you need to focus specifically is the FRP, which is highlighted by the red, which is encircled by the red circle. The FRP is basically an abstract value determining how on fire a certain area is. Each of these 17 million data points correlates to a polygon in a certain region and time, and it also has a neighboring polygon, and it lists both their FRPs. So the plan was to use these 394 values to calculate the FRP of the neighboring polygon given a specific time one day after. And I accomplished this using a simple dense neural network, because there are a number of different variables that weren't directly interconnected. And after roughly 67 epochs, we reached a 92.5 accuracy, which is pretty good. Finally, moving on to my goal 3, which is forest fire risk assessment, I found a dataset called Wildfire Prediction Satellite Imagery on Kaggle. It was roughly composed of 42,000 images, roughly a bit more than half classified for wildfire events, and roughly a bit less for non-wildfire events. These were essentially satellite imagery shots of specific areas in Canada. They were all set to be 455 pixel size each, and the goal was to essentially take this image and then train a neural network and spit out if it's a wildfire, if the area would turn out to be wildfire or not wildfire. And I accomplished this by using 4 layers of convolutional networks, increasing in filter size and continuously max pooling, eventually feeding it to a dropout rate, and then 300 and the next layer 300 nodes to smooth out the curve and make it more efficient before our final dropout layer, and finally the dense neural network to classify as wildfire probability and non-wildfire probability. And after roughly 50 epochs, we reached a surprisingly good 95% accuracy, and overall taking 2 hours. So in general, we accomplished our goal, and we were able to train 3 neural networks to holistically assess wildfire risk, detection, and spread. If you want to find datasets and train models on your own, you can use this repository that this QR links to, and So some of the limitations of this project were that, well, I relied on satellite imagery and human gathered datasets, which have some level of noise and inaccuracy, and also doesn't account for, let's say, low ground fires that can't be detected from these sources. I also had hardware limitations. I used Google Colab, which offers roughly 4 CPUs of power, which isn't that much when you consider how much data you have to process. And also, of course, my project is limited only to the North American continent due to data constraints and, of course, hardware limitations. So conclusions, future work. I hope that this project will serve as a solid foundation for others to use for wildfire detection in North America. And in the future, I hope to work on a general model that incorporates not only all these three goals together, but also expands the datasets to global levels. And again, impact, I hope that this will provide a foundation for others and help prevent global warming through cooperative research. Thank you.